Cool. So let's get started today. My name is Amar Srinivasan, and Jamie Sampson and I together are presenting towards deep learning models resistant to adversarial attacks. Thank you guys for joining. Cool. So largely our agenda today follows three segments. We'll be broadly talking about what an adversarial attack is, why they're important, and then again, how we can defend against them. And that last part will have the experimentation and results from the paper. So broadly, let's talk about what an adversarial attack is. So let's talk with this super simplified example of supposing we first have an input image and a traditional CNN classifier. And let's say our classifier has only two classes, one being a gibbon and one being a panda. So for every image, we try and classify whether it's a gibbon or a panda. And now let's suppose that we have an input image. If you mind just clicking through, Jamie?
Sure.
So we have an input image that's a panda, and it reports 57% confidence, and so we classify it as that. And then suppose we add in a small bit of noise, and think of this as just random colors across each color channel, and we do a small perturbation onto this original picture. The output is going to look very, very similar, as you can see from the original example. These are pretty much the same image, but it's very strongly confused our classifier, and now this reports a 99% confidence as a given. This is the definition of adversarial attack on a computer vision network. However, as of right now, you guys might be thinking, okay, interesting, it still looks like panda to me, shouldn't be a concern. But if you go to the next slide, we can see sort of a real life case where this might be an issue. So let's say we work at a company that uses eye tracking security to make sure that we are who we are when we log into our computer. And let's say I pull up an image on Google Images and I try and match it up. It gives me a 23% match. Maybe using an adversarial attack, even though the image looks the same, the computer recognizes it as a completely different person, matches it to me, logs into my computer, and has all my credentials. So this is why adversarial attacks are actually important and are real concerns we should be worried about. So you might be wondering, how exactly does this happen? You know, the image pretty much looks the same. And so let's suppose we have a network here that has this kind of decision boundary, where the green images on the left are perhaps pandas and the right images are gibbons. So in the center, we can see all the bounding boxes around each of those images. Let's call those all the bounding boxes we understand as the same thing. So for example, everything around a green circle is everything that looks like that green circle. So as you might imagine, because these computer networks don't actually know what a panda is, and that's their goal of learning, there could be the case where something does seem to look like that for us, but happens to cross the decision boundary. And so according to the right image, you might say, well, that's fine. Why don't we just construct a more complex decision boundary? And okay, yes, I agree with you, but it'll take a little bit of work to get there. So that's what our paper today is trying to answer. Basically, what is an adversarial attack and how can we defend against them? So as we can see there, the first problem in our paper is that we need to understand what an adversarial example is. You know, we just kind of added a bunch of random colors, but perhaps there's a more rigorous definition that'll be able to fool computers more often. And then the second component is how we can train a model such that given the inputs and given the capacity of our model, we have no more adversarial examples, meaning that if you want something to look like a gibbon, you have to pass in that sort of image and not just an altered panda. So the authors call this an optimization problem, and there's two that they talk about. The first is the inner maximization problem, which tries to find an adversarial version of a given point. So we can think about, you know, things that are from Google Images that still look like that Google image that achieves a high loss. And in that case, that is just a misclassification. And the other problem is the outer minimization problem that tries to minimize the error of the model parameters so that we can have a robust model that performs well. And so let's just briefly dive into the math behind our attack definition. So originally in a model, we want to minimize the expectation of the loss, where the loss is defined as a function of three parameters, one of those being our data matrix, the other being a vector, and then theta being our list of model parameters. Obviously, you know, the networks that we've built in Fellowship AI are a lot more complex than that, but that's sort of the mathematical simplification from there. And then so the L function is our chosen loss function. So that's kind of our original model goal. But now when we're considering adversarial attacks, we want to consider new inputs where we replace X with X plus some other parameters. So the paper proposed two definitions for adversarial inputs. The first one is the fast gradient sign method, which by definition includes the gradient of the loss function, or the direction at which the loss is changing the most, as well as the sign of that loss. So we can construct areas at which the loss is changing the largest around a certain image, and that epsilon value is going to be imperceptibly small to where we can't see that. Likewise, with the projected gradient descent, again, won't delve too much into the math here, but fundamentally we want to find inputs that are seemingly close from a gradient perspective, but still are actually maximizing the loss that we can achieve. And so now we've understood what a good attack is, and we want to be mindful of creating a strong defense. So one proposed defense in the paper against adversarial attacks is just to increase the amount of data in our training set, right? Sounds easy enough. If you have inputs that aren't classified well, why don't you just include those in your training set, and then your network will understand how those work. And so the paper proposes adding those FGSM or PGD inputs to the training data set. And if you were to comb through these either on Platform AI or just go through them yourself, you might wonder, why do all of our images look the same? And that's exactly the kick, is that remember, they're all supposed to look the same, but they are mathematically different in their construction. And of course, this relies heavily on having what we call increased network capacity. And I would think of this as just like deeper models, right? Let's say you have like a 2 or 3 layer model that can't necessarily understand all of the inputs, or worse, actually ends up fitting to the inputs more so than the original images. So they're not going to properly learn the perturbations or the fact that they are representations of the same source image. But again, we don't want to lean too hard in the other direction. I put an image of the bias variance trade-off. So, we're not going to put 250 layer models in something that's a Panda or Gibbon classifier. We also want to be mindful of the fact that we're not overfitting to our training data set and that we're able to understand variability.
Okay, thanks, Amar. I'll talk a little bit about some of the experiments that were done in the paper. But before I do that, I just want to talk a little bit about kind of the approach and the objectives. So the authors, obviously built off of, other cited papers and knowledge around this subject. And their objective was to define a theoretical framework for adversarial attacks. And they got pretty specific on what they defined as the attacks that this approach would defend against. So they talked about previous work was kind of like virus protection, where there's a certain virus introduced and the virus protection companies go out and quickly develop the antidote for it and then get it into their product and update their product. They kind of looked at adversaries a little bit more broadly. So they talk about first order attacks, and one of the key and interesting things about a first order attack, just like in the formulas for fast gradient sign and projected gradient descent, you saw the loss function. They sought protection against those attacks where the attacker has has access to specifics of the model, i.e. the loss function, et cetera, et cetera. And then from that, they logically conclude that, well, if we're protecting against an adversarial attack for someone who has knowledge of the network, obviously we're going to be protecting for black box attacks. So that's kind of the framework that they worked with. One other point that I want to make too is there were a couple places in the paper where the authors stated some facts, made a conclusion. I'm sure people familiar with the cited papers kind of understand the chain between the assertions and the conclusions. For some laymen, such as myself, I had to kind of accept their conclusion and trust, they're in a peer-reviewed paper, and I'm sure that conclusion is, validated. So you might not find on specifically one slide, you might not be able to find a direct connection based on the output of an experiment to the conclusion that's reached. So I just want to give you a little bit of heads up on that. So here's the first thing they looked at. So what they were looking at is, how can I say it? They were looking to establish that it's possible via adversarial training. That means adding training instances that were developed. And for this experiment, it was specifically using the projected gradient descent method, that a model trained on those instances would be robust and protect against any and all first order adversaries, i.e. Adversaries that relied on information specific to the model. So not just the inputs, but also the gradients of the loss function with respect to the input. So if we look at the diagrams up here, we've got two data sets that they worked with, MNIST and CFAR10. What they did is they did standard training. So that's training on instances as we would normally recognize. They also did adversarial training, did a version of the model with adversarial training. And that's where they took the original instances, applied the projected gradient descent on them, and then use that as part of the training as well. And so you'll see the 3 bullet points. Those are observations that the authors made. I won't read them, but you guys can read those briefly. But the important thing is the next point, that what this demonstrates is that robustness against a projected gradient descent adversary will yield robustness, i.e. protection against all first order adversaries. So, the key thing there is it will cover attacks by adversaries familiar with the gradients of the loss function respect to the input. And naturally, if it protects against that, it's going to protect against black box attacks where the adversary doesn't have any knowledge or direct access to the target network. And again, this is a point where I had to trust the authors and the previous cited papers, to make that leap based on this information. Okay, this is another experiment that highlights the point that Amar made about network capacity. So we've got, if you take a look at the first 3 charts above, so the first chart represents standard training, so no adversaries involved. And there are 3 lines related to the inputs. So obviously, the blue line, which is the natural inputs, the model does very, very well, near 100% accuracy. But since we have no training on the inputs from the 2 adversarial attack approaches, FGSM and PGD, the accuracy is very low. The second and especially the third chart are more interesting. If you take a look at the third chart, what you'll see is the third chart is where the model was trained, including the PGD generated data. And you'll see that as the scale of the neural network increases, especially around 16, we suffer just a tad bit on the natural data, but you'll see the accuracy obviously is much higher for the FGSM and the D data. So the main point of that is, especially when we start, when we incorporate the projected gradient descent data as part of our training set, it also will provide some protection against first order attacks, as the authors expected that it would. So what this slide does is it specifies in the source column different source networks used for an attack. Where you, and of course we've got two charts here, one based on the MNIST data, one based on the CFAR 10 data. And so the first source is the network itself, and that's a white box. So that's saying the attacker has knowledge of of the network and the loss related to the inputs. And you'll see pretty good. And then the method, this relates to the training method. So naturally, if you take a look at the top row in the chart on the left here, you'll see you've got extremely high accuracy, 98.8 for the natural method. The accuracy decreases a bit when we augment the data with our adversary data, but still remains relatively high. There's one, the outlier here, PGD with 100 steps and 20 restarts here, we're starting to dip below 90%, but that appears to be an outlier for that one. So, and then the second source is, how can I call it? I'll call it a clone of the original network. So it's a network of the same architecture, but was initialized independently and trained independent of the original network, network A. And again, we see pretty high accuracy on the MINS data set. For each of the training methods. And then the third one is there's a paper, the space for transferable adversarial examples, and that paper talks about, in essence, it lists several architectures used to kind of initiate an adversarial attack against an original network. So they tested the best one of those, and again, we even using that as the source, accuracy remains pretty high. And just throughout this, the authors acknowledge that accuracy is higher on the MNIST data set than the CFAR for this experiment and for most of the other experiments. Okay, let's talk about conclusions. As Amar mentioned, the network capacity alone increases the robustness against these attacks. The FGSM, fast gradient sign method, is a one-step method. Especially for larger perturbations, this network training using the FGSM generated input didn't increase robustness like the projected gradient descent did. And back to the formula, if you look at that formula, it's a little bit more involved. It relies on not just the loss and the gradients relative to the input. It also relies on the previous instance of the input as well. So it's a more complicated adversary. So training using PGD input definitely adds value. But as to point 3, it does not add value when the network is not sufficiently large to accommodate that. And the main point here is, without considering adversaries, we might look for the smallest network, the fewest parameters to train that, you know, meet our classification objectives. But that in and of itself probably won't make our network, you know, resilient against these first order adversaries. And then the fourth point is, so even using the PDC adversarial model, the saddle point problem, which is the kind of the balancing problem that was mentioned, the min-max problem, the value of that decreases as we increase the capacity. So for a given set of generated PDC adversarial data and regular data, we'll get better performance as the you know, as the size, the depth of the network increases. And then the fifth point is that more capacity and stronger adversaries decreases transferability, meaning training a second network and using that to try to generate instances that will, in essence, break the original network. One other point I wanted to make is, so the paper is very theoretical, but there are some very practical things that can be considered, especially for models like the one that Amar showed, that where accuracy and being able to protect against adversaries is key, i.e. security applications, retinal scans, et cetera, et cetera. So that's it. Any questions? And of course, we'll post the slide deck to the Slack channel. All right, if there are no questions, that's it. Thank you very much.
Thanks, guys. Take care.
Thank you.
Thanks.